Good morning, friends. So, in the last lectures, we completed sharing stresses. So, that's why today I am starting. Our fifth unit is the that is torsion, and after that we will study column and strut. So, that's why today first we will start torsion. So, what is mean about the torsion? As you know, in the beams, when the load is acting around the beams, so because of the deflections of the beams, means that is bending stresses occurs in the beams, and because of the bending stress means the effect is the bending stresses induced in the beams. So, because of the twisting of shaft, effect is torsion. So, that effect is called as torsion. So, as in workshops you studied the shafts, that is the lathe machine shafts etc. Or yes, torque is applied. So, yes, when the suppose this is the shaft, and when equal and opposite forces equal and opposite couple actings on the shaft, so this twisting moment occur in the shaft. So, that is nothing but it's a because of the equal and opposite forces, that is called torsions of the shaft. So, the note down. Suppose this is a rim. On this rim, here force is applied. This is force and this is radius. So, the product of turning force and the distance between the distance between the point of application of force and the axis of the shaft and the axis of the shaft is known as torque, or twisting moment or turning moment or twisting moment. This is called twisting moment, and the shaft is said to be subjected, and the shaft is to be subjected torsion. So due to this torque, every cross section in the shaft is subjected to shear stress. So we will study this shear stress. So in the torsions, some of the assumptions is to be considered. So that assumption in torsion. So first assumption, the shaft is above the uniform circular section. The shaft is of uniform circular section throughout. So the cross sections above the shaft, that is to be assumed that this is the uniform circular sections throughout. Next, the material of the shaft is uniform. The material of the shaft is uniform THROUGHT throughout. So this is throughout. Now third assumptions. So yes, the cross sections is assume this is the uniform, and the material of the this is the you can say this is homogeneous or isotropic type. So that's why the material of the shaft is uniform throughout. The normal sections, cross sections of the shaft, the normal cross sections of the shaft. So this is remains plain before applying above the torques, and after applying of the torques remains same. The normal cross sections of the shaft which were plain are which were plain and circular before the twist remain plain and circular after the even after the twist. The shaft of the, so this is third point. The twist along the shaft is uniform. The twist also is assumed to be uniform throughout the shaft. So last point, so the normal cross sections similar to this, all diameters of the normal cross section which were straight before the twist remain straight with their magnitude underchanged so this is unchanged, so this is not unchanged, unchanged after the twist. So these are the assumptions that is to be considered during the design up of the shaft. So next is the torsion equation. So next is the torsion equation or torsional stress and strains. So consider this is a plane. So here's the shaft is fixed. So this is cross section. Now length of the shaft. This is C point and this is A point. So that's why here also this point is O. Now suppose due to the applications of the torque, so this is twisted and this is A dash. So here this point is the O, this is A dash, this is A and this angle is the theta and this angle is phi. So this is for understanding purpose. Suppose this is twisted. So that's why here consider a circular shaft fixed at one end, fixed at one end, subjected to a torque at the other end to a torque at the other end as shown in figure. So this is T is the torque in Newton mm. L is length of the shaft in mm. R is radius of the circular shaft in mm. As a result of this, so this O2A, this is shifted to the O2A dash. So that's why let angle ACA dash equal to phi and angle AOA equal to theta. Tau is shear stress induced at the surface surfaces. So this is intensity of the tau, and this is greater at the outermost fiber. C is or G modulus of rigidity, also known as torsional rigidity of the shaft material. So that's why here strain, as you know, strain equal to deformation and divided by unit length. Deformations divided by unit length. So that's why this deformations A to A dash, and this is divided by unit length L, and this is equal to tan phi. So this phi is small, so tan phi equal to, you can consider this is phi. So that's why phi equal to A dash divided by L. We also know that length of arc of contact equal to, so length arc of contact A dash equal to R into theta. So that's why this is again phi pi A dash or R theta divided by L's, or you can consider A dash equal to, because this is, since this is A dash equal to R dash L phi equal to. So next, so this is first equation. So tau is the intensity of shear stress in the outermost layer. In the outermost layer means in the outermost. So this layer, in the outermost layer, and C is modulus of rigidity of shaft. So that's why this is phi equal to tau divided by C. This is second equation. Now by equating equation 1 and 2, so here you will get relations tau divided by C equal to R the theta divided by L's, or tau divided by R's equal to C theta by L's. So this is the important relation. Shear stress above the outer fibers, and this is the maximum radius, modulus of rigidity, and this is the theta, angle above the twist, and L is the length above the shaft. So these relations tau divided by R equal to C theta divided by L. So this is important. So actually torque equations tau theta divided by R C theta divided by L is equal to T divided by polar moment of inertia. That we will see. That is the polar moment equations. Now strength above the, so what is the strength above the solid shaft? Strength of solid shaft. So consider this is the cross sections of the a solid shaft, and this is the elemental area dA. So this elemental area dA, and this thickness is dx, and this distance is x, and this radius is equal to r. So consider a solid cross section having small elemental area dA, having thickness dx, having thickness dx and distance of area from the shaft center is x. The shaft radius is r. The shaft radius is capital R. Now the elemental area dA equal to, so this is dA equal to, this is small dA, 2 pi x into dx into dx. And shear stress at this section equal to tau x equal to tau into x divided by r. So tau x is shear stress developed at the outermost fiber, and tau x shear stress developed at the elemental area. About elemental area, dA have distance x from O. So that's why tau x equal to tau into x r. So turning force equal to, so shear stress multiplied by area. So that's why shear stress equal to tau x or tau into x multiplied by dA or tau divided by r into x into 2 pi x into dx or 2 pi x square into dx. So this is the turning force, and turning moment equal to turning force multiplied by distance of element from the axis of shaft. So axis of the shaft. So again this is, you can write this is 2 pi into tau divided by r's multiplied by x square into dx multiplied by x and 2 pi tau divided by r's into x cube. Now the total torque, so this is equal to torque. The total torque is with the shaft can which the shaft can withstand may be found out by integrating the above equation. So that's why total torque T equal to, so this is 0 2 pi into tau divided by, this is r x cube into dx. So that's why 2 pi tau into r. So this is x raised to 4 divided by 4 0 and this is capital R. So this is 2 by tau divided by 4 r into r raised to 4. Alright. So this 1 r will get cancelled and this is pi into tau into r cube divided by 2. T equal to, so now T equal to, by putting pi into tau, this is d by 2 capital D by 2 cube equal to pi into tau divided by 2 d cube divided by 8 or T equal to pi by 16 tau into d cube. This is the relation, or same you can write tau equal to 16t divided by pi d cube. This is the popular relation. So tau equal to 16t divided by pi d cube. This is the strength of the solid shaft. Now if the strength of the, this is the now hollow shaft. So hollow shaft means here and so this is capital R and this is small r. The shaft radius r is shaft outer radius and inner radius is small r. So for hollow shaft, now by using same, so use this relation again tau equal to, this is same. So only change here, so this is turning moment. So here's integrating, so this is instead of the 0, now this is r and this is small r. So that's why this equation becomes 2 pi tau divided by r, and this is capital R r raised to 4, small r raised to 4. So this is 1 by 2 pi into tau divided by d raised to 4, small d raised to 4, and this is capital D raised to capital D. So that's why here is multiplied by 1 by 8. So you will get relations 1 by 16 pi into tau D raised to 4, small d raised to 4 divided by capital D. This is the relation. This is for hollow shaft. So try to note down this. Consider a solid. So instead of the solid, this is hollow cross sections having a small elemental area. Having thickness dx and distance of area from the shaft center is, or shaft axis is x, the shaft outer radius r and inner radius small r, dA equal to. So this is, try to note down this equation. So this is for hollow shaft. So this is for T equal to for hollow shaft. Now next definition is the polar moment of inertia of shaft. Or polar moment of inertia. So polar moment of inertia, and this is the moment of inertia of a shaft of plane perpendicular to the plane of figures, that is called polar moment of inertia. So the moment of inertia of a plane of a plane area with respect to an axis perpendicular to the plane of figure is called polar moment of inertia with respect to the point where the axis intersect the plane, where the axis intersect the plane in a circular section or circular plane, in a circular plane. So this point is always the center of the circle. This point is always the center of the circle. We know that. We know that. So this is tau divided by r equal to c theta divided by L, and so tau equal to, we know this is 16t divided by pi d cube from strength of solid shaft equation. So that's why, suppose this is first equation and this is second equation. Now by putting a value of tau in equation first, so this is 16t divided by pi d cube multiplied by r's, and this is c theta divided by L. So that's why this is t divided by pi by 16 into d cube multiplied by r into c theta divided by L. So this is t divided by pi by 16 d cube, and this is d divided by 2 equal to c theta divided by L. Now this is pi by 32 d raised to 4. So here's t equal to polar moment of inertia, or J equal to c theta L, or t divided by J. So where t, or this is polar moment of inertia, IP, or J is polar moment of inertia. So that's why now this is t divided by J equal to c theta L, and c theta L is equal to, as we know, tau divided by r's. So that's why these equations becomes tau divided by r's equal to c theta divided by L, and this equation is known as torque equation. So the whole chapters of the torsions, that is the based on these relations, T divided by J equal to tau divided by R is equal to C theta divided by L. T is the torque or twisting moment, J is the polar moment of inertia. So tau is the shear stress. So here's this is tau is the T is the torque or twisting moment, J is the polar moment of inertia, and tau is the shear stress is acting, R is the outermost radius above the outermost fibers or radius above the shaft, C is the modulus of rigidity, theta is the angle of twist, and this is in radian. Otherwise, I will write here. So this is T divided by J equal to tau divided by R is equal to C theta divided by L, where, so this is most important equation because whole chapters this is based on this equation, where twisting moment or torque, this is in Newton mm or Newton meter. J is polar moment of inertia, unit mm raised to 4, shear stress of outer fiber from the axis, and this is equal to Newton mm squares or megapascal. R is outer radius. So same equations is applicable for hollow shaft also. So J equal to polar moment of inertia for hollow shaft. This is different. So outer radius of shaft, C is modulus of rigidity, and this is also in gigapascal or megapascal. Theta angle of twist in radian, and L length of shaft in mm. So this formula is very important because whole chapters that is the based on this equations, that is the torque equations. So be careful about these equations. Multiple choice questions may be asked. T divided by J or polar moment of inertia, tau divided by R, C theta. Definitely this 1 mark or 2 mark questions will be asked on this equation because theory related with this our subject is very less. So that's why be careful about this equation. So due to limitations of the time, today I stop here and we will continue problems related with the torsion we will solve in the next class. Thank you.